All right, we've now got part 4 complete, so let's go ahead and come over here to our implementation plan overview and mark it off. No one guy we can circle, so I guess we can just walk right on down the list. So we've got our 3 primary things knocked out. Now let's turn our attention over to part 5. The goal in part 5 is to create a fully functioning enemy. In order to have a fully functioning enemy, we need the ability to have enemies spawn into the scene randomly, meaning in random locations. Then these enemies must be able to move around at different speeds and in random directions. And of course, when the enemies are spawned into the scene, they need to scale into existence, because in the end, remember, we want them to appear as if they were climbing out of a cell that has just died. And then finally, we need to make sure we have this nice little method created that will allow us to add X number of enemies at any given time. We can just say, look, add 5 enemies. Boom, there's 5 randomly placed enemies, and all is good. So that is the overview of what needs to be accomplished in part 5. Let's go ahead and just clean that up real quick. Jump over here and pull up a fresh screen. And here we go. All right, let's put 500 fresh screens in there. Let me just drag that one out. There we go. So here we are, part 5. And in part 5, we are looking at implementing enemies. All right, so that is the goal of this section. And there's several things that we need to look at. Now, instead of jumping right into the implementation plan the same way I've done the past 4 implementation plans for precision, let's do this a little differently. So instead of saying we're going to add this field and we're going to add this field and we're going to do this constant and that, let's do it a little differently. How about this? Let's talk about the objective and break the objective down. Our objective consists of 4 key things that we need to have take place for this implementing of enemies. The 4 key things are, number 1, spawning. Obviously, we need the ability to create enemies in the scene, but we need the ability to create X number. So X number, so however many we want, 5, 10, 8, so X number of enemies, and they need to be placed randomly. Okay, very important. So now we've got enemies spawned in. When they spawn in, they must be able to scale up. So on spawn, scale from 0 to 1. Okay, so that way it looks like they are, well, again, climbing out of a cell. Okay, so they're going from a size of 0 up to a size of 1. What else do we need? Well, once they have been born randomly around the screen, they now need to start moving around. But there's an interesting thing. While they're scaling, we don't want them to move around. We want them to be harmless as they scale up to their normal size and then start moving around. So in the end, what we're going to do is implement a system that is going to make sure that we cannot be harmed by an enemy that is growing up, if you will. He's spawning into existence. But while he's spawning into existence, we don't want him moving around either. So we need to make sure that the enemy cannot move while scaling. So cannot move while scaling. And then finally, now they can move. That they need to move differently. They need to move in random directions, different amounts, and at different speeds. So let's just put down random movements. Different speeds. I'll just put diff speeds. So there you go. This is our primary objective for part 5. The question is, how are we going to pull it off? So let me give you a diagram. So here we go. For entertainment purposes only, there is our screen. So what happens? They spawn up, random locations. That part's pretty easy. Once they've scaled all the way into existence, now what do? They begin moving. We talked a little bit about the movement system when we provided the implementation overview, or excuse me, actually we talked about it there and a little bit in design as well. We talked about the way we wanted them to move is this point A to point B system, starting out where they are. Consider that as point A. We want to be able to randomly generate a point B. Then we want to basically say, over X amount of time, travel to this location. Okay? Once they hit this location, now pick a new random location, and this will become B, and this B will become our new A. And then, of course, once again, let's come up with a time, and the journey begins once again. And this just continues. They just keep moving around the screen. You can't kill them. Once they've been spawned in, they're there. Your nanite probe doesn't have the ability to knock them out. We have the ability to slow them down when we get to the very end of precision and we implement the power-up system and we put the time power-up in place. But right now, our goal is simply going to be keep away from them, because if they touch us, they will kill us. So they're just kind of wandering around, and that's what we're looking for. We didn't want to put any kind of seeking AI on there, because what would happen? They would all just start merging on to you. So basically they're merging onto this one point, and it doesn't really look good. So then you have to go in there and put a lot of variation in, start changing the times up even more, and even then it just turns out to be a whole pack of these guys just kind of following you around. And it doesn't have a really nice look, and not only that, it's easier to play that way, because you can kind of lead them all in one direction, then quickly run over to another area, and they start to turn around and head back. This way, it's like a moving minefield, and the whole idea of the game is precision. And so the idea that Logan and I came up with is, well, let's just have them wandering around, because now you're really going to have to be cautious as you're moving your nanite probe.
Right. I really am happy with the way that the swarms end up occurring, because as you get into higher levels, you'll have maybe 6 to 10 enemies on screen, and the movement is almost deceptive. Sometimes the enemies will simply get slower, because a few of them will reach the end of their one movement span, so you'll see an opening appear, and all of a sudden that opening will close up as you try to move through it. Because you have 5 enemies you didn't realize were going to pick a new location start to move.
Right.
So I mean, it really does make a very dynamic field for being such a simple game.
And as you start getting up to the higher levels, it could get very tricky, that's for sure. So, basically, if we come over here, take a look at our 4 objectives. The spawning thing, that's going to be easy. The scaling, we've already implemented that. So we just need to hook it up more or less once we get enemies in place. Cannot move while scaling? That's going to be easy. So this entire section is really about movements. How do we pick point A and a random point B? Then how do we make the actual enemy move in a predetermined amount of time from one point to the other? That is what we need to understand here. So we're dealing with some animation once again. So back a couple sections back, we dealt with flicker animation, we dealt with the scaling animation. Now we're dealing with some movement animation, and we're going to show you the system that we're going to use to do this. It's a very simple system, but we want to break it down, make it as clean as possible here in this implementation plan before we jump over to code and Logan starts putting it all together. So once again, prepare yourself for what could end up being a kind of lengthy video. All right, so now that we have our objectives, and we know that we are focusing on this part. This is what I'm really going to be harping on in this video right here, okay? Everything else is a no-brainer, and you guys know how that kind of stuff works. So we're just going to simply say, create a new enemy and make the enemy scale up over X amount of time. Again, you guys are familiar with that stuff. So movement is our primary focus. So how do we make the movement system work? We're going to start out by making 2 static utility methods in the game class. And these static utility methods are going to provide us with some information that we need that is going to make, randomly selecting locations very easy and generating random numbers, random float numbers between a given range that we provide easy. So we're going to start out. Let's go ahead and start jotting some of these things down. I'm going to break all of this stuff down for you. So we're going to create 2 static methods in the game class. And by the way, right now, let's just take a moment and talk about something, Logan. For those of you out there that have done some object-oriented programming in the past, and perhaps you're just a little bit past or even way past where we are right now in the XNA 101 class, and you're wondering to yourself, why are we putting this in the game class? Why don't we have some sort of utility class or a helper class, or why don't we have a scene manager, or why are we doing it like this? Why are we putting the giant switch statement in updates? I'd like to remind everyone that the XNA 101 class is just that. It is an introductory class. And this is really the very first game, very first truly object-oriented game that we have done with XNA in this class so far. So we're still trying to keep everything very simple. We don't want to really start piling on complex techniques and complex styles of programming games. Not yet. Let's slowly build this stuff up. So you'll notice with Precision, what we're doing is we're using everything we've seen through Volume 1 and Volume 2, and now we're starting to throw a little bit of math at you. We're starting to throw a little bit of, hey, here's how you can animate something over time by doing the flicker control, the scale control, or now some movement control. So we're starting to focus on some other key elements that are going to become important in most any kind of game you're going to create. But things like management systems, utility helpers, things like that, we'll get to those things. So I just wanted to throw that out there real quick, Logan, because here we are putting two static methods in the game class. And this, in the end, might be something that you as the programmer decides to do. It might just be a real quick thing, and you may not have a bunch of utility utility methods that you need to group together in a particular class. And in our particular case, we only have two. But I just wanted to throw that out there real quick, that as we progress into some of the more sophisticated games, we are going to start shifting gears and get into things like scene managers, etc., etc.
Right. The idea is here that for Precision, we've kind of created a delicate balance between framework versus functionality, in that we didn't want to get so deep into framework setup that we lose focus on some of the specifics, some of the subsystems we have to create.
Exactly.
So what we're going to do is leverage the fact that Precision at its heart is relatively simple, and therefore we're going to keep it, I would say, kind of lean on the framework side, so that we can focus on some specific concepts with animation without having everything getting kind of blurred. Because, we could take the whole framework aspect very far. We could get into a scenario where we have a completely general-purpose 2D engine, but we would spend so much time in that we'd lose focus on the game at hand.
Exactly.
And those things can be saved for the future. Once we have the basics down, we start to get you could say we've got our chops established in basic mathematic functionality for animation. We have kind of a toolkit we're assembling. Once we get some of those basics out of the way and we're ready to play and play faster, we can get into things like heavier frameworks so that we can have a more extensible engine.
Exactly. Well said, Logan. Well said. I just wanted to point that out. I thought that was really important because we haven't really taken the time to say that. And, so far between Volume 1 and Volume 2, I don't know if you knew this, but we're breaking 80 hours. We're right at 80 hours or just over it right now. Isn't that cool? And after 80 hours, some people might be thinking, I've got some programming experience, and why aren't you doing this? Well, because it's still a fundamentals class. We're working our way to that stuff and past that stuff. Okay, so attention back over here to Part 5, implementing enemies. So we're going to create two static methods in the game class. These are utility methods. Get random screen position, and it's going to take in a padding. And range, it's going to take in a min and a max. They've seen range before, haven't they, Logan?
Right, we had that Pong knowledge review.
That's right.
And that was one of the things used to... honestly, I can't remember what it was used for, but I know it was useful because I needed a min and a max for something.
And so we set up a...
speed or a direction.
Exactly.
For direction, I think. Variation on, direction.
Actually, it was, now that you say it. And so there you go. So we've seen this before, though we didn't really break it down because it was a knowledge review. We'll break it down here. So what are the purposes of these two guys? Well, the get random screen position, he's going to return a vector 2. It is basically a position somewhere on the screen. So some random position on here, which means, of course, inside the get random screen position, we're going to be taking into account two things. Actually, three. We're going to take a look at our screen width, our screen height, and we're going to be dealing with a particular sprite at the moment because we want to make sure that when we're grabbing a random position somewhere on the screen, we don't want the random position to be in such a place that you end up with the sprite drawn like this, partially off screen. We want to make sure that there's enough padding in there that that can't happen, that the furthest over we could draw would be that. Or if we were perhaps up in the upper right-hand corner, that would be the furthest over that we could draw. So we want to make sure that padding is taken in, which is really going to be nothing more than the radius of the sprite itself. And remember, we set radius up as a property on our actor. So that is what we're going to use get random screen position to do. Who's going to use it? Well, we're going to use it in two different places. Basically, we set up a set random move that we talked about back in the implementation overview section. And set random move is going to take an enemy and say, okay, point A is going to be where I'm at right now, and point B is going to be some random place off in the distance. Well, guess what? How do we get that random place off in the distance for point B? Simple. We call on get random screen position to give it to us. So that's why this guy is going to become important. So he's going to be used by the set random move over an enemy. Also, couldn't we use this with our add enemies method that we set up? Remember, we wanted to be able to spawn X number randomly. Well, what if we had a loop that said, let's spawn 15, so we now have a loop that loops through 15 different spawnings, and each one that we spawn, we then call upon get random screen position to pick up some random location to set the position for the enemy to. So there's the two reasons we're going to be calling upon get random screen position. Now we've got range. What do we need range for? Well, range basically is going to return a float between a min and a max number. So, in a few minutes, we're going to need that ability. And, ta-da, here you go. We can pull it out of range. So in a second, we're going to take a look at what the insides of both of these look like and exactly what is happening and why and how they all interrelate with one another. So this is the first thing that we need to do in our implementation plan. Why? Because we know we're going to need these methods. Let's go ahead and get them in place so that when we start coding over inside of the enemy class, these utility methods are available to us. So far, Logan, everything I'm saying pretty clear?
Yeah, perfectly clear. I mean, we're just laying down some of the things that we'll need to build upon in order to make enemies work.
Exactly. And that, you know what? That was horrible.
That was the most awesome line ever.
Well, thank you, sir. I'll buy your lunch tomorrow, just for saying that. All right, so now... All right, that's a little bit better. Okay, so the first thing is creating these two methods. What's the next thing that we need to do? Well, we're going to turn our attention over to the enemy class. And inside the enemy class, we have that set random move function just sitting there. That method needs to be implemented. So let's go ahead and jot that down. So now we are inside of the enemy class, and we need to implement the set random move method. And once again, in enemy. Well, what is he going to do for us? He is going to set point A. These should be some members that you might remember creating when we went through and skeletoned everything in. He's going to set point B. He is going to set the move time, where the move time is going to represent the total time that the move is going to take. And then finally, he's going to set, boy, this is one of the most important ones of them all. Okay, they all are, but this really is important. It's going to set the amount member to 0. Ooh, that's so important. Here's what's going on. When we get in here and we start looking at the code, basically we know that we have an enemy right here. We need the enemy to go somewhere. So how are we going to pull this off? Well, let's go ahead for just a second and provide an overview of this. I want him to go to some random location. Well, I can call on my real good buddy, get random screen position, to give me some random location. So it's kind enough to do that for me. It's just giving me a random position. All right? Set random move is going to take where I am, I being the enemy, and it's going to set my current position as point A. What that means, ladies and gentlemen, is point A equals my position. Okay? Then it's going to randomly generate point B, thanks to that utility method. Then I'm going to come up with a move time. Now we're going to see where range is going to come into play, because we have a base speed, but we also have a variance. So now we can say, all right, use range. Okay, that's great. We can go between, this much below and this much above our base speed. Here you go, range. Could you please give me some random number? Thank you very much. Now I have the speed. So let's say I ended up getting lucky. The base speed, let's say, as an example, was 9 seconds, and it gave me 1 second back. I now know that I've got 10 seconds to get from point A to point B. Now, how do I make this happen? Check this out. We have linear interpolation. We have used linear interpolation in a couple of our smaller projects a few times. Linear interpolation, we're dealing with, interpolate between this value and this value. Well, we're going to use a form of linear interpolation here, but we're going to change it up. Let's just drop the word linear and add the word smooth, because linear interpolation looks like this. Let me draw you a couple pictures, because I love drawing pictures. I'm going to draw you two graphs. Okay, on these graphs, let's say that point A and let's say that point B is at the top. So point A, point B. So I want to get from A to B, but I need to do it between 0 and 1. This is kind of the control. This is the driver, if you will, for the movement along. Here's what I mean. Linear interpolation. I'm going to start at A, and I want to get to B by the time my driver is at 1. Okay? So what's this going to look like? Well, if it's linear interpolation, it's going to be a straight line that's going to go there. So I have some control number that is slowly getting bigger, going between 0 and 1. And as we go between 0 and 1, it can basically sample where I should be and give me that information, as you can see right here. So if I was to start out at position 0, and let's say I'm going to go all the way up to 10, if I was 50% of the way, where am I going to be, Logan?
On your driver?
Yeah.
Then that'd have to be at 0.5.
This will be at 0.5, and where am I going to be if I actually took a look at, in this case, the line I've drawn?
Then you'd be at position 5.
Yeah, it'd be half the distance right here. Okay? So 1/2 the way. Then divide it by 2. Now, pretty simple. Simple interpolation. Interpolating between two values. In this case, the two values are point A and point B. Location A, location B. Okay? Now, smooth step looks a little different. Same exact principle. I'm going from 0 to 1. That's my driver, if you will. But what happens is I generate a curve that looks like this. That's pretty close. This is basically a cubic function. What's taking place here is it's an ease out. Okay, so as we're coming out of our starting point, we're starting from A, we slowly start to ramp up. Now we're going as if we were linear. And then right before we start to go in, we ease in. So if I was to see this in motion, and once we code this, we'll be able to show it to you as well. If we were using linear and we were going from point A to point B, then to a new point, then to a new point, it would be very solid, very just like we just bounced off a wall. Okay, there is no easing into that and back out of that position. So we're going to use smooth step. It's going to give us a very smooth transition, okay, into the position we're going to. And then, of course, now we're going to a new position, so we're going to smoothly ease out of that position, pick up speed, and slow down as we go in. And what this is going to do is it's just going to make it look smoother. It's going to look nicer. But this is what our curve looks like. So once again, if we start out right here at A, as our driver goes forward, we begin moving towards B, but look at this, we're not moving as much. Then we start to pick up our speed. Here we are once again at the 0.5 mark, and we are 50% along the way, and this would be 5 again, okay, if we were going up to 10. Now let's continue on, and as we get up here to 0.8 and 0.9, we start to slow down. Less changes are taking place now as we approach our final destination. So that's what we're going to get out of smooth step. So smooth step is going to be our driver where we can basically say, look, we're going to do a smooth step. And with smooth step, what we want to do is we want to go from point A to point B. And now we need some sort of control. This control is that guy I was showing you up here that goes from 0 to 1. Control is amount. There we go. So this number needs to change every time the enemy's update hits. Because as long as this number is changing, we can use smooth step to interpolate between this location and this location smoothly. And we can get that position out and set our enemy to that new position. And this will have our enemy moving. So obviously, this is going to be taking place inside of update. But you can now see why setting point A is important, point B is important, and why setting amount to 0 is important. Because anytime we begin our move from point A to point B, the driver always needs to start out at 0. Because when we are at 0, we're at point A. And when we are at 1, we are at point B. And when we are at some number between 0 and 1, we are somewhere between the two. Okay, very important stuff to keep in mind. And again, you're going to see this broke down in just a second when we pull up another sheet. Logan, is there anything you want to add to this?
The idea is that amount can be viewed as a percentage. That's the reason it goes from 0 to 1. 0 being the beginning and 1 being the end. Or rather that it has a, or was I looking for? I guess just the beginning and end concept. That we go from
0% to 100%.
Exactly.
Except the numbers are represented with 0 to 1. Very nice. So we're going to get all of this set up. Now move time, of course, is going to be very important because move time is going to need to affect the amount so that basically we go from 0 to 1 over the time we specify that it needs to take to get from A to B. That's where move time comes in and is very important. At this point, I've probably given you enough clues that you can actually code this, but we'll go ahead and continue forward. All right, so we need to get all of this set up, and once this is done, this basically has the set random move in our enemy class done. Now, of course, we're still going to stay inside the enemy class, but then we're going to turn our attention over to update. So in update, we're going to add in some code. Basically, we need to increase amount. That is so important. You know what? Let me put it another way. How about this? If I can undo back far enough. I'm just going to put INC. Increment amount. I like that better. We need to increment our amount. We have to. We've just shown it to you right here. It has to get larger every single time. If it doesn't get larger, then we're not going to be moving. All right, so let's see. What else? We need to make sure that we set the position. So every time in update, after we increment that amount, we're then going to turn around and set our position. Okay? And then, most important part after getting the position set is we need to make sure we check amount to see if we've hit 1. So check amount for 1 or greater. In case it hit like 1.001 or something. Because if we've hit 1 or greater, we have managed to make it all the way to point B. We don't need to try to move any further. We're there. So at that point, if we're at 1, guess what we better do? We better go ahead and call set random move. Because what's set random move going to do? It's going to set point A. Well, what's point A? Point A is where we are at. Chink. Then it's going to set point B. Where's point B? Well, it depends on what get random screen position gives us. Some random location. Then we need to come up with a new random move time using range and our base speed and our variance. And then we need to, here it is, set amount to 0. And this is then going to, in update, allow us to start tracking from our point A to our new point B. Okay? So let me see if I can undo a couple of those things. Whew. All right. Now, after we get this stuff in update, everything is going to be moving around just fine. And we're then going to come in here and we're pretty much going to wrap things up by adding just a couple more things. Don't think you guys are about to get off the hook. You have that fast forward button on your video, so you can feel free at this moment to fast forward or even hit stop. But after I draw these next 2 things up, then we're going to go over to the whiteboard and we're going to talk more about these methods that we're going to put in there. You don't mind, do you, Logan?
No, this is good stuff to establish because
much detail as we can provide.
This might clear up some of the mystery because at this point we've used things like your random screen position, but not gone into too much detail.
Exactly.
I mean, we know what it needs to take into account, but not how.
But we want them to see it. All right. So after we've got all of this taking place, we now can test out and we can see an enemy randomly moving around the screen smoothly from position A to another position, easing in, easing out, etc. Then what we need to do is go ahead and have our enemy scale in. And then we need to make sure enemies cannot move while they're scaling. And this is really easy to set up. And you guys know that we already have implemented a scaling system, so we'll just simply use it. And then all we're going to do is turn around and we're going to use a property that we're going to set up called isHarmful. And isHarmful, well, if one of our guys, an enemy, is moving around the screen, he is harmful. That means he is not scaling because he's moving. Okay? So if we are scaling, he's not harmful. So just put that in the back of your mind. We're going to be coming in and dealing with a property called isHarmful, and that's going to be the heart of making this part work. But that's really simple stuff. That's just establishing a property and setting it. So now what I'd like to do is go ahead and jump back up here and spend a couple of minutes talking about some of these methods and what's going on inside of them to make them work. So first thing let's focus on is that get random screen position. So to do this, let me come over here and bring up another whiteboard real quick. All right, to save everyone some time, let's not worry about writing part 5 up here. Let's just jump right into it. So here we are. I'm going to create a public static vector2 get random screen position. And as I said on the other board, it's going to take in an integer and we're going to call it padding. Now what takes place inside of here? Well, it's real simple. All we're going to do is generate a new vector. So we're going to return, because that's all we need. We need some sort of random XY position that represents a location on our screen. So we're going to return a new vector2. Now, this new vector2, what's the X component? X component is a random value. So we're going to use random. Remember, we've already set that up. Fix my A a little there. There we go. So we're going to use a random dot next. And this is why I'm drawing this out. This is what I want you to see. We need to start off at padding. And we're going to, so that's our minimum, and we're going to go to our screen width minus our padding. Okay, that gives us our X random number, comma. Let's go ahead and jump down here beneath this, do our second one, our Y, random dot next, and once again padding, comma, screen height minus padding. Close it off, terminator, and now let's go ahead and finish off the method. All right, let's talk about what's going on here. Now, in the past, we've gone over random, and we've talked about inclusive and exclusive. This is very important. When using this overload, this guy right here is inclusive. That means that this number is a possibility that can be returned from random. Now the next number is a little bit bigger because we have an expression over here. This number, the second one, is exclusive. This means that we will not get this number back. We'll get everything up to, but not including this number, okay? That's very important. These things are going to play out a role in just a second. Now, let me take just a minute and see if I can draw a halfway decent looking screen here. I'm actually going to reach over and grab the old shift key for this one. Hey, Logan, I might just actually pull this one off. Ooh, so close, so close. All right, ladies and gentlemen, this is our screen. We are running 800 by 600. Okay, so there is our screen height. This is our screen width. Here is our sprite. Let's just say that our sprite is 40 wide. I'm just making up numbers now, okay? By 40 high. Fair enough?
Sure, that's certainly a possible value. Just set the texture to that size and you'd be ready to go.
Now, when we created the property for radius, what did we say to do? Remember, we set this up during the skeletoning in phase, and inside of actor we said, all right, everybody's going to have a property called radius, so all actors. And what did the radius give us? It gave us 1/2 of the texture's width, right? So the radius would be equal to, in this case, since remember, all of our sprites are circular based, even though they're still indeed squares, they are circular. And that's why we can get away with doing this. So here we go. So half of this is going to be a radius of 20. Okay, keep that in mind. Now let's take a look at what gets returned from getRandomScreen. We first need to come up with an X. So right now we're focusing on this line right here. So X. X is give me a random between between padding and go all the way up to screen width minus padding. All right, well, what is padding? Well, if we were to use this sprite example and we were to call get random screen position and send the radius in, we could then say padding is equal to 20. Okay, because remember, I am stipulating right now that I made a call to the get random screen position method, and I passed in the sprite's radius. So padding is now 20 inside this method. Excellent. Now, generate a random number. It could be padding, because padding is inclusive, so it's between this number and the next number, but this one's inclusive, so it could actually be this. So that means in the x direction, we could have 20. So starting right here. So we'll say that this is 20. Of course, my scale is all blown out here, but you get the idea. So between there and screen width, so now we're looking at this part, screen width minus padding. So what do we have? We have a screen width of 800 minus our padding of 20, which leaves us with 780 pixels. Okay? So we can go between 780? No, that's exclusive. So it would actually be, since this is integer based, 779. Okay? So 779 is right here. So we actually have 21 pixels to the edge of the screen right there. Now, that's all good. We have figured out an X location. Now let's take a look at our Y location. That would be this guy, the bottom half, okay? Again, starting at padding, we want a random number for Y. Starting at padding, which is 20, since that is inclusive, the first number, we're going up and down now, okay, because we're dealing with Y, so there's 20, all the way to the screen height, 600, minus our padding, 20. So what are we looking at? 580. But once again, minus 1 off of this. Why? Because it's exclusive, so 579. So we are right here, 579. What have we just done? Well, we have just created kind of like a border, if you will.
It's almost like we've created a shrunken rectangle of the screen dimensions.
We have, absolutely. Let me draw this out real quick, guys. Bear with me. I'm hurrying. Almost there. Now, here comes the cool part. Almost there. Faster, 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 faster. Okay, here it comes. My sprite, 40 by 40, has a radius of 20. If I tell my sprite that, let's say that the number I got back happened to be padding by padding. Okay, so I got 20 by 20 back. Well, where am I going to draw my sprite then? Well, I'm going to use the origin, which is the center. That would be right here. Check this out. Look where my sprite drew. Did any of my sprite go off the screen? No, it drew perfectly on the screen. Okay? So that is why we have set this up with padding. That padding prevents us from having a situation where we draw like this. We don't want to run into that kind of situation. Now, I've taken the extra effort here to point out the fact that the second part of the next method is exclusive. What does that mean? That means if we were to draw at 779, we are 1 pixel shy of going off. Now, I wanted to point this out. We could, of course, add 1 if you want to be perfect. Let's stop for a second and think about what we're using this for. We are using the get random screen position for generating a new point B as our enemies are moving around, or for picking a location on the screen for the enemy to be randomly spawned at when the game begins. That's the only two things we're doing. Is this 1 pixel offset going to hurt us? No. Will a player ever see this? No. Because as soon as they scale in, they're moving. Everybody's constantly moving. So you're not going to see this. So just in case you happen to be watching this and say, hey, there's a pixel you missed. So we know. Do we want to do the extra calculation? It's not necessary. And that's something, while right now we're not yet talking about optimization and really getting into optimization, because once we start doing that, we're going to start coding a little differently. But here is an example. If you'll never see it, why perform an extra step or an extra operation? That's just a waste of CPU time at that point. Okay? So this is how the get random screen position works. So basically we can call upon it, we can send in a radius, and it will give us back a vector2 that will give us any random place on the screen where we can safely place a sprite without risk of it being drawn partly off screen. Whew, that's one out of the way. The next thing. Not boring you yet, am I, Logan?
No, just one thing I wanted to point out with
yes,
that.
Sir.
Also, the whole idea of taking in the padding was to keep the enemy placement on screen.
That's
entirely
right.
on screen. If we're an extra pixel to the left, an extra pixel on screen, we have still succeeded at keeping the enemy on screen.
Absolutely. It has done its job. All right, so let's go ahead and hide this guy out. And let's go ahead and come up here real quick. The next one that I wanted to talk about was range real quick. We've seen range in the Pong game, but we didn't really talk about what was happening. I want to show people what's really happening inside of it real quick, because now we're into true theory lecture, and all the idea is for everybody to, gain a lot of knowledge from this stuff. So here we are with a public static. Once again, we're making these static because they're going to reside inside a game. We're not going to be instancing the game class, and we need to be able to access these two utility methods from other locations, such as enemy. Okay, so public static is going to return a float. It's going to be range. And we're going to take in a float min to a float max. We want to be able to basically say, look, give me a floating point number, give me a float that's between this number and this number. Here you go. Thank you very much. That's what we're looking for. So inside of here, all we're going to do is simply return we're going to cast it to a float because, well, we're about to get a double out of this. That'll guarantee it's going to come back as a float. But we're going to do random. So once again, random's already been set up. We've set it up. We're going to do next double. So next double. Then we're going to multiply this by, to make this number work properly and it be between min and max, we're going to say max minus min. Then we need to step it back up, so we're going to say plus min. And that's it. Let me show you how this works. Hang on. There we go. So let's say that I have a max of, 20 and a minimum of 5. So I want something between 5 and 20. Of course, once again, just like in the last video or a couple videos back, Logan, I'm not going to put 0.0 and all that. Everybody just stipulate we're dealing with floats when they get returned back, okay? So, check this out. With next double, we're going to get a double back between 0 and 1. So here we go. 0, follow me here on how I'm writing this out, to 1. Okay? Then we're going to multiply the result of that 0 to 1. Now remember, I'm looking up here, so there we go. 0 to 1 multiplied by max minus min. So 20 minus, let's just do this, max minus min. And what's the result of that going to be? That's going to be a 15. So let's take all of this and solve it. This is going to say between 0 and 1 times 15. Well, that's solvable. that means we end up with a result of 0 to 15. Because the low end, 0 times 15 would be 0. The high end is 1 times 15 would be 15. But now let's finish off the equation. So now we're going to say plus min. So let's go ahead and say plus min. What does plus min mean? Well, that means we're now going to shift, because what is 0 plus 5? Because min is 5. So now that we've seen that, let's go ahead and just write 5 in here. So 0 plus 5 gives us a possibility of 5, and 15 plus 5 gives us a possibility of 20. Ladies and gentlemen, we have just returned some number, some floating point number that resides between 15 and 20. That look pretty clear, Logan?
Yep, simple enough. The idea is, so another way to step back through that is that next double gave us a range. It gave us a range of 0 to 1. What we were looking for was a custom range. Not only just a custom range, but a specific starting and ending point for that range.
Exactly.
So not a zero based, but a possibly offset based. So the first thing we need to do is we have a 0 to 1, and that's a range, but it's not the range we wanted. Fortunately, it is 1 base, so that can be very easily multiplied. So what we needed to do is to take that 0 to 1 range and find what our real range was. What was the actual range of our min-max span? And to get that value, we need the difference between min and max. That will give us our actual range. That's why we subtract min from max. That gave us our range. And that gave us a range we could multiply. That gave us our 15. 15 is our new range. If we multiply that by next double, now we have a range of 0 to 15. So we cover a unit base of 15.
Exactly.
But we have a minimum to consider here. So we need to take that entire range and then offset it by minimum. Minimum was given as 5, so we shift that entire range up 5, and that gives us our final range of 5 to 20.
I'm jotting in some of your terminology there. And exactly, and there we are between 5 and 20. So, of course, if we end it up with like a 0.6, that 0.6 gets multiplied by 15, and then we get 5 added to it, and we get the proper number sent back out. Okay? Beautiful stuff. So that is how range works. So now we're about to see these guys get put into action, because now we need to take a look at how set random move works. So at this point, we just finished the second of the 2 utility methods that are inside the game class. Let's go ahead and come over here and bring up yet another whiteboard. All right, so now let's all pretend that we are in the enemy class. Except let me not draw it like that, because that looked awful. All right, in the enemy class, we have skeletoned in a method called setRandomMove. Doesn't do anything at the moment. Now, we said a few minutes ago when we were laying out this implementation plan that setRandomMove was going to set point A, point B, move time, and amount. Let's take a look at it real quick. So basically what we're going to do is we're going to create a private void, because it's not going to return anything back. setRandomMove. And inside here, here's how we're going to set point A. So point A is going to equal our current position. I'm just going to refer to these members directly, which of course you can. When we get over there and start coding out, you'll find us using this dot position. But we're talking about our current instance ourselves. So we're equal to where we are, our position. Point B, what did I say point B was? Point B was some random location on the screen, but within the safe bounds so that we don't accidentally draw part of it off. How do we get that? Simple. We call game 1, because we haven't changed the name of it. That's what he's called. So game 1, that class, that's our game class. The static method, get random screen position. And we're going to pass in our radius. Once again, this dot radius. Okay? So we pass in radius. So get random screen position takes that radius in as our padding, and it finds out here's where you're going to be. Again, a random position on the screen that's using the screen width and the screen height and this radius to calculate where. It returns it back, and we store that information in B. Now we have a destination to go to. Okay, so far so good. Now we need a move time. Now the move time is how long is it going to take for us to get from point A to point B? Okay, how many seconds are we looking at? Now, we have a speed already, a base speed. So let's use that base speed. So let's start with a base speed. Then, if you guys recall, we created a speed variation. Okay, so we said enemies are going to move at this base speed, but they can variate this much plus or minus. So here's what we're going to do. We're going to turn around and we're going to call on game 1 again. And we're going to use the other utility method we set up. We're going to say range. And we're going to say, with this range, give us between negative speed variation and positive speed variation. There you go. So if we said that the speed variation is, let's say we said that the base speed is 5 and the speed variation is 1. That means we could be -1, +1. Give us some random number between there. And that is what range is going to do. And that's what we just got finished explaining a second ago. So this will set up our move time. And it is, like I said a second ago, it's the time it's going to take to get from point A to point B. The final thing that we need to do in set random move is set the amount to 0. So 0F. This is important. Remember, amount is our driver for our smooth step function call. And starting out at 0 means we start out at point A. So this is it. That's all that needs to be done inside the set random move. Very good. Now we need to move down to update. So I'm just going to put update here. We know it's being overridden and everything else. And I'm not going to worry about any other code that might reside in it. Let's just start writing from right here. So update, what's going to be in here? Well, first of all, check this out. If, this is so important, move time is less than or equal to 0, we better go ahead and get some sort of new position to move to, which is going to generate a new move time. Because a move time of 0, what? An instant teleport? Or not to forget, in a second we're going to have to divide by move time because we're going to need to divide time up. So we don't need a divide by 0 problem. That would not be fun. So basically, if move time is less than or equal to 0, let's just go ahead and get another move time by calling set random move again.
Because in this case, we're going to consider anything less than or equal to 0 to be an invalid move time. 0 would, in essence, represent moving at infinite speed. We don't have a case to handle that. And less than 1 would represent moving backwards in time.
Exactly.
And we don't have any case to handle that. So we're going to say that the movement mechanism is going to require a positive amount of time to move by. Precisely. And if that wasn't provided, then attempt to get another random move. And the reason to reattempt is that when you're tweaking base speed and speed variation, you could come across a combination that would result in some possible hits of 0. What if the variation could bring the speed lower than base speed? Or what if you had more variation than you had base speed? That would mean 0 is a possible result, or less than base speed would be a possible result.
Exactly.
So we want to have it set up to handle this. Now, it might not look as graceful as you might want. You might have enemies that would snap around the screen, but at least you won't have enemies that disappear or code that crashes.
Okay. Enemies that jump around the screen, well, position, here's the good thing. Back up and set random move, we're always going to set point A to where we're at. So that's going to be a good thing. So we're always going to say start out from where we're currently at so that we don't get any sort of weird snap like that.
So I guess that means just we'll avoid cases where they disappear. I think what I was getting at is with the possibility of hitting 0, you could hit some very small fraction above 0, which would be valid and would be an incredibly fast move. Maybe
I
over
see what
1
you're
or
saying.
2 frames.
Yeah, absolutely. And that is very true. Okay, so now that we've got this taken into account, let's go ahead and look at what do we need to do next to make this guy move because we're inside of update. We need to look at amount. Because remember, what is amount? Amount is our driver. So amount is going to be incremented, so plus equals, and I'm going to use the game times elapsed game time in total seconds once again, and we talked about this in the last section that the elapsed, or actually a couple sections back when we was doing the scaling and all, elapsed game time is the time since the last update, okay? So we're dealing with a very small slice of time. Once again, 0.01666666666667. There you go. So what we're going to do is we're going to use that. So let's come in here. We're going to go ahead and cast it because we know this returns a double. So a float. Instead of writing out the whole thing, Logan, let's all stipulate that I just said game time dot. Now I can write all this out. Elapsed game time, because this is the guy that we're most interested in. Dot, I'm going to get this in total seconds. All right. Now I need to do something with this. I need to take into account the move time, because the move time is the total time that we want it to take. So if I was to take this here and divide it by move time, I'm going to get what I'm looking for. Okay? Let me see if I can give you an example. So let's say that we have an amount. Amount must go from 0 to 1. Right? We all know that. That's what we're driving. And my move time is 10 seconds. Let me see if I can find a place to draw all this. Let me do right here. I think I can make this work. All right, so amount needs to go from 0 to 1. And my move time, I want the transition to go from point A to point B over 10 seconds. Okay? Now remember, let's not lose sight of what it is we are figuring right now. We are figuring amount. That's what's important here. So, it needs to go from 0 to 1, 0 being point A, 1 being point B. So, if we were to take a look at a slice of time, we've got 0.0166. We'll just stop right there. That's this guy. Okay, because we're running 60 frames a second. If we were to take that and divide it by move time, we're dividing it by 10. What this is going to give us is our increment here of 0.001666666666. Basically, we just moved the decimal point, okay? Now, that's what we've got. Now, what if we were to take this, so this is the amount. That amount changes each update. It's a very small fraction. So once again, as this guy's our driver, point A, point B. Every frame, this guy's incrementing this small of an amount. Okay, because remember, we want this, in this particular case, we want this move to take 10 seconds. We're firing at 60 frames a second. That's 600 frames that we need to go through, okay? You see what I'm getting at here? 60 in 1 second. So this is the small amount. That amount is changing. So the amount that's changing each second, so in a full second, how much has amount changed? Well, all we need to do then is just pull this guy on down and say, what is our 0.00166 times 60 of these? Because that's happening every single update, so every slice. Well, if that's happening every single slice, we need 60 of those slices to be a full second. So that's going to equal 0.1. Okay? So now I can say, well, we move 0.1 every second. Amount changes. I don't want to say move because that's not the right word there. Now I'll explain that in a second. Amount changes every second. Okay, so here's where we can check our work. How many seconds did we request this guy to move over? 10. So what is 0.1 times 10 of these? Well, guess what? Just move that decimal place. It's 1. What was the value we were trying to go from? We started out at 0. We know we did. We initialized it to 0 right here. But now we need some way to get it to 1. Well, we've just seen that this line right here will slowly increment us up all the way to a value of 1. Why is that important? Once again, looking at the graph, you've got point A, point B, starting out at 0, at a value of 1. Boy, my drawing skills aren't the prettiest today. There we go. Again, we're using smooth step. So as that amount value changes from 0 to 1, we are interpolating, we're getting a vector back that's interpolating between point A and point V. And what we're seeing is our enemy is moving from its, so here's our enemy with his little spikes. He's moving from one location to another location. And he's being driven there by amount, 0 to 1. There we go. We just saw how we got to 1. Okay? Logan, is there anything you want to add on top of this? I thought working through with the math might help people see it.
What that made it look like is it was kind of breaking it down backwards, so breaking it down to the individual amounts. And not only that, the reason that it needs to be broken down, because total seconds by itself would do just that. It would move by a second. That means all of the enemy movements would be 1 second. Move time is what gives you the configurability to get different move times, because we saw how we had broken down the individual elapsed, which was the point 0166, and then divided that down. We gave 10 seconds. We saw that gave us an even smaller value. And then we showed that incrementing that would give us smaller increments, but if we added all of those increments up, added them all together, we ended up with a movement over 10 seconds, which was the desired thing from the onset.
Exactly. So there you go. We now have an amount that's changing every update in the enemy's update. Yes! Now we need to use it. Watch how easy this is. Remember, we're the enemy. We have access to our position. So what if we were to say take our position and we don't increment to it, we just outright set it. Set it to vector 2 dot smooth step and once again this is where we say we're going from point A to point B, and our driver is amount. And we let the smooth step method calculate exactly that interpolated amount as our driver amount changes. Okay? Taking us from point A to point B. It's really as straightforward as that. But now we need to make sure that we find a new location to go to once we reach our target area. Okay? Because now we need to start heading into a new point B, because this point B needs to become point A. So what we'll do after this position is we'll just simply say if the amount is greater than or equal to 1. Now, why did I say greater than or equal to? Well, we're doing a plus equals. We could have ended up just a fraction of a hair over 1. So if we are greater than or equal to 1, this is a question. Have we reached point B? Question mark. If the answer is true, all we have to do is call set random move, and that's all. I'll go ahead and close off update. If I call, well, that's a horrible curly brace. If I call set random move, what do? I say point A is equal to where I'm currently at. So point A just became what point B was. I then say point B equals some new random location, thanks to our utility method getRandomScreenPosition. Then I come up with a brand new random time. So I may have just got to this position quickly and turn around and move to my next position slowly. And then I reset a mount, which is where it's all at. I put our driver back to point A, and that's where we're going to start from. And then update will turn right around the very next iteration through and start moving us again. Okay? That is the moving system in careful detail. All right? So that leaves, looking at our implementation plan, only one thing left to account for, and that is our add enemies. So let's just, for this one, instead of doing a new screen, let's just kind of scroll on down, and we'll just talk about add enemies because it's really straightforward. And we know add enemies takes in a whole bunch of stuff. It takes in, well, let's see, the number of enemies you want to add. It takes in the texture. It takes in the base speed, the variation speed. It takes in all these things that the constructor needs to initialize and that number of enemies. Well, we're going to use that number of enemies in a loop. So we're going to come in here and do one of those good old for loops where we're going to say for int I equals 0. So we're going to start out at 0, and we're going to say while I is less than the number of enemies you want on the screen. So while that's true, just keep incrementing I. So check out how easy this is going to be. Basically, we're going to come in here and we're going to say make a new enemy. Oh, suddenly I forgot to spell enemy. That was pretty funny. So enemy equals new enemy. Now, why are we actually doing this? Because we know he just got thrown into the list. So that's all good. We can get back to him. Why did we hold a reference to him for just a second? Well, simple. Well, of course, don't forget, we're going to send the texture, the speed, and all that stuff. Okay? We held the reference so that we could turn right around and say, look, take this brand new shiny enemy and set its position to, you probably guessed it, game1's dot get random screen position and let's make sure that we look at or send to it our radius or his radius. There's a D in there, I promise. Okay? And that's it. So we create the new enemy, we hold a reference to him for just a second so that we could turn right around on the very next line of code and randomly position him somewhere on the screen. By implementing this add enemies method, we now have the ability to simply call upon it and say, look, add 10 enemies, and these 10 enemies will be randomly distributed throughout your screen. Logan, anything you want to add to this?
No, it's really just as simple as that. It's just basically combining 3 ideas. 1, make enemies. 2, position enemies randomly. 3, lots of them. Do the same thing for however many times we want.
Exactly. So, ladies and gentlemen, that's it. That is what we are out to accomplish here in Part 5. So in the next video, Logan is going to code all of this up. And by the end of that video, we will have functioning enemies spawning on the screen. They're going to be scaling up from 0 using the scale system that we implemented back in Part 3. And they're not going to be harmful nor moving while they're scaling. Not that harmful is a big deal right now, but we'll be getting to that in the next section. And yeah, that's what we're looking for. So with that, that is going to wrap up this video. Thanks a lot.